Right. So as I mentioned, I added like a couple of more slides to the lectures, simply because remember at last time when we ended, we were seeing situations like this. Remember, we're saying that, well, we can clearly see. So this is doing the expected response, right? We're like estimating the expected response, looking at the different value of x. We're looking at log income to be 1579, and then we are having 5,000 parameter draws for all of the parameters. So in theory, what we're plotting here is once we do the expected, so we wrote a function, and once you write out, like say we're evaluating the mean because we're looking at the beta 0 value plus the x value times the beta 1, and we have 5,000 of them, right? So once we write this function, and then you evaluate it at the 4 different values of x, you're having 5,000 different values for each of the x, and we're talking about the mean. Okay, and that's what we're evaluating. And we came to this point last time that we're seeing an interesting trend that clearly the mean of the means are shifting to the right when you increase the log income, which is not surprising because you have, what is it, beta 0 plus beta 1 times x, right? And we have, I think, about 0.4 in terms of the median of the beta 1 estimate that we have. So it's not surprising that when you increase your x, the whole expectation will increase, right? So that's what we see here. But we were, I guess many of us were surprised and curious about, well, they're all 5,000. So all of these density plots, the 4 of them, they're all plotting 5,000 values, okay? And we not only see the trend about the mean being increasing, but also about the spread being decreasing, right? So if you look at the spread, well, it's more varied when income is low, at least among the 4, and then it's less varied, it's more peaked and like a smaller or smaller, like shorter width of the density plot that you do. So I think that's where we left last time. So I'm going to give you a couple of more minutes to discuss with your neighbors to see what you think. And you will see that. So what I would say is so if you go to Moodle to access the new slides, I added one more because I was curious. Well, what if I choose a different set of x values and see what we get? And I'm choosing 10, 11, 12, and 13, and this is what we got. Okay, so together with this, and I will recommend you to maybe go back to this plot a little bit more and think about if you can come up with a reasoning of why we're seeing that kind of decreasing trend. Okay. Okay, so let's hear from some of you. I guess we can take this together, like the one. This is the 1579, and this is the 10, 11, 12, 13. And from this, do you see any? Like, can you provide some reasoning of why we're seeing this trend of in this way, and in this particular plot is shrinking in terms of the spread, right? Whereas on this one is expanding overall. I guess between 10 and 11 is not a big difference, but yeah. I should just mention this earlier, I overheard those discussions. So we are using the same beta 0 and beta 1 every time. Okay, it's the same set of 5,000. Okay? Yeah, it's the same set, but it's just changing the value of x, which is the log income. And then we start to see the difference. So what do you think? What do you think is driving all of this? I can come back to this plot a little bit. So this is just plotting the log expenditure against the log income with, I think it's the first 10 lines that we can fit. So again, the lines we're talking about because we're getting 5,000 posterior draws for each of the parameters as a triplet, right? We have beta 1, beta 0, and then sigma. So what we're doing, this plot is taking the first 10 pairs of beta 0 and beta 1, and we just fit them. Okay? And what do you see, like something special about the line in some way? So there are 10 different lines, it's hard to see. But there are 10 different lines here. and many of them are overlapping, but they still have some kind of feature, I guess, together with the cloud of the data. Yeah, Jonathan.
Well, it's just more dense in the middle, and then it's less dense as it widens out. As you can see, the lines.
Yeah, so if you look at the cloud of the data, it's definitely like the majority, or like there are a bunch of observations in here, right? Whereas a fewer elsewhere. And if you look at the feature about, because all of this again is beta 0 times beta 1x, right? So there are 10 different lines here. Many of them like having a big overlap in the condensed area, right? Whereas you're gonna have like a larger spread once you are having, like say, not in the condensed area, but like when you have fewer data sets, or sorry, fewer data points, right? So from this plot, what you can see is, well, the model is reflecting the fact that for some of the X, you have a bunch of data, where like in this majority over here. And then you will have less uncertainty about the beta estimates, right? Because you can see that the 10 different lines are concentrating, intersecting a lot, very condensed. But then when you have fewer data points for some other values of X, you start to see the variation of the estimate of beta, okay? It's being reflected in the lines that we see. So if you want, using the R script that I posted, you can actually try not the first 10, but maybe the next 10 or even 50 of them, you will see a bigger variability overall, right? So that's actually, I think, giving us some indication of what is happening in here. And so keep in mind what we have. So this is when it's 1, 5, 7, 9, right? And the next is from 10, 11, 12, 13. So keep those numbers in mind. If we come back to the scatter plot that we had at the beginning, so the 1, 5, 7, 9 is actually in this range, right? And then the 10, 11, 12, 13 is in this range. Okay? So overall, I would say in the first range that we're looking at over here, the smaller the log income, like the smaller the value of X that you see, the fewer data points there are. So there are higher uncertainty. Okay? So that's why you see 1, 5, 7, 9 as the value increases, the spread of the density plot that you have is decreasing because you gradually get more data. Okay? Whereas between 10, 11, 12, 13, I think the majority, I mean, it's bigger over here. I think more data points over here. And then you have less as you increases. So that's why on that plot, you see that the first two, when it's 10 and 11, I mean, the spread is not that different from each other, right? Because the number of data points might be very similar to each other. But then when you increase your value of X to 12 and 13, you're having less data points, fewer data points. So you are having higher uncertainty in terms of estimating the beta and beta 0 and beta 1. So that's what you see this kind of trend. Okay. So yeah, so taken together, I think this 1, 5, 7, 9, and then this 10, 11, 12, 13. You can actually plot other ones that you like after class just to see how things work. But I think taking these two together, and then especially looking at the scatter plot of the feature of the data points, as well as the 10 different lines that we fitted, we are looking at spread as it goes away from the cloud. I think taking all of this together, giving us some ideas of why we're seeing that trend. So again, when you have more data points, you will have less uncertainty in your estimates, and that's true for the Bayesian estimation as well. Okay, in some frequentist methods you learned before, you probably have known about this feature, but as we can see in the Bayesian paradigm, we can't have a bunch of draws about betas or like any other parameters, and then it's still affecting in terms of how large data sample is or the subsample is. In our case, looking at this is depending on like around the X value, how many observations you have, and then the larger the number of observations, the lower the uncertainty you're gonna have for those estimates. Okay, okay, yeah. I should mention the reason why I pick 1, 5, 7, 9 as well as 10, 11, 12, 13 is mostly because, at least the way that I figured out using the GG ridges, GG ridges, the package, I guess I didn't figure out how to like read label them in a sense that like I want them to be increasing on the y-axis is 1579, right? And then we can see it on the x-axis as well. And so if you pick say like 10, like 9, 10, 11, 12, then 9 will come last because they're gonna start with 10. Yeah, for whatever reason. So if you figure out how we can make that work, that might be useful. You can let me know. But the reason why I'm picking this ones here is mostly because we can see the trend more clearly, like gradually as we want to see it, right? And all right, so for the expected response, if we come back to the one, oh, this is the one, okay. Yeah, so the 10, 11, 12, 13. All right, so I changed it. So I guess I don't have the same numbers anymore, but this is the one that I have for the second set that we did. Okay, so you can also return what we call the quantile, right? We can look at the median, the middle 95%, 90% cardinal interval. So if we have a different table about the 1579, you can see you can interpret those expected log expenditure in terms of what the values that you get. So I guess instead of 5, because we don't have it on this slide anymore, let's just say 12, then you can get 9.38 as the log expenditure, the expected value of the median of that, right? And then all of this will be the other things that you can do, okay, about the middle 90% credible interval. So yeah, so that's another summary you can do in addition to doing the GG ridges and then showing all of the expected value, how you can make those. Yeah. So from the expected value, what people usually do is to do prediction. So expected value is just expected of y, right? But we care about the future prediction of yi itself. So what you do is pretty simple to what we similar to what we did before. You go back to the data model. So the data model told us that it's equation 19 on the screen, that we're having independent normal with individual specific mean, which is beta 0 plus beta 1 xi, but then we also have the standard deviation sigma being estimated. So earlier, what we've been talking about, those plots and stuff, is about estimating this, the mean. But if you want to make a prediction, you just take one more step, because you can generate a new data point from the normal model with the mean that you estimated before, and then with the sigma that you have from the MCMC. So the thing that I write over here is when you're looking at the variability in the prediction, not only you have variability because of beta 0 and beta 1 from the expectation, but also you have the variability from sigma. And so all of this together contribute to the variability in the future prediction that you make. So in terms of like how to make it work, you simply just take one more step. So remember in the past when we were covering like beta binomial, all those models, we listed out like a graph like this, like say you simulate like the parameter and then you simulate a new draw, right, in terms of the prediction. What we're doing right now is you simulate the mean, like what we already did, like 5,000 of them. And for each of them, you can just take one more step using the R norm function to make a prediction, like what we used to do. Okay, so in this case, because we have saved 5,000 draws, I think, for each of them, beta 0, beta 1, and sigma. So when you do prediction, if you want to use all of the parameter draws that you have, you can go up to 5,000 predictions that you do. Okay. But you can pick other values as well. Maybe you don't want that many. Maybe you only want to do some of them. But the number of parameter draws you have is 5,000 for each of them. So in theory, you can go up to 5,000. Okay? But you can rerun the JAX code and then get more parameter draws if you want to get more predictions. But this is the procedure. So what I want to show you is you can write a different function that not only you get the mean, like what we did earlier. Okay, that's the beta 0 plus x times beta 1, right? You can now just take one more step doing the R norm function. Okay, so I'm doing 5,000 of them because I have 5,000 parameter draws. And what I do is I fit the mean here and also give the standard deviation from the MCMC output. Okay. And then you can put, so again, the example here I'm using is 1579. So you can do that prediction pretty easily. And you can either just plot them again. So now this time you don't see that much variability in terms of their spread, right? But of course, overall, if you have larger log income, then you will have a larger predicted log expenditure. Okay, so that's general the trend, and you can also return plots like this. I would say like tables like this that you're looking at the median as well as the 90% credible interval of the prediction. So one thing I would like to mention, is earlier when we're looking at only the mean value of log expenditure, this is the credible interval that we have. Okay, that's only looking at the mean, and that's only taking into account the variability of beta 0 and beta 1. Okay, and now what we're doing is we are having a prediction, which is from a normal with expectation of y and then sigma, right? So naturally, because now we're incorporating more variability in the prediction, you will see a bigger spread in terms of, well, if I'm fixing the same x, I will have a wider spread of the predicted values of y comparing to my mean, okay? And that's what you see here. So earlier, when your log income is 5, 90% credible interval for the posterior expected log expenditure is 6.25 to 6.62, whereas if you're looking at the prediction interval, it's much wider, okay, when you're working with the same log income to be 5. Okay? So this, again, I think reinforces the ideas that we are introducing one layer of variability, and that's actually embedded in the model. And the predictive distribution incorporates this uncertainty in the log expenditure represented by the standard deviation sigma. Okay? So I want you to get the sense of how different ways of or different sources of variability come into play, and then you can actually visualize it or like compute it and then just make a direct comparison. And then you can see how different pieces of the model come together. Okay? Yeah, so you can try with other values later if you want, but this will be some basic code and basic approaches that you can look at this. So what I would do is for the next, I think, let's see,